Just checking if the voice is working. Okay, it seems to be working. Great. So welcome back to my Blaze engine stream. I'm going to continue with what I started last time. So last time we were working on getting GLTF models to be loaded in the system. And so currently this is what we can see, just turning it on. So we see this weird cube that doesn't render properly because parts of it are in different order of rendering, let's say. So the face that is currently in the back always shows up at the top because the rendering is done in the order in which it is submitted instead of what is in the front. So the first thing we will do is get that corrected. So each of these objects will actually show in the order that they are, right? So currently, if you can notice the rotating panels, the panel on the left side is always drawn over by the panel on the right side. And this progressively goes on because the order of rendering is from left to right in this case, mostly because the entities were created in that order. What I will do here instead is get a depth buffer, and I'll explain how that works as we go. But a depth buffer effectively just prints the depth or the distance of the pixel from the camera in each frame. And so when it tries to render, it just checks if you're drawing ahead or behind. If you're drawing behind something that's already been drawn, then it skips it. If you're drawing ahead of it, then we draw over it. And we'll see how that actually works when we go through the render doc debug. So yes, I'll actually go through the inner workings by using render doc. And in fact, we can do it just now. Hey, Unhinged. Glad to see you back. So we can start with actually just debugging this first. Not debugging, we don't really have bugs at the moment, but just seeing how the frame is captured or the frame is rendered. So as you can see, you have some overlapping from the left to right. So we can open this color pass, and here's the thing. It first renders the one on the left, then renders the next one and the next one. And you can see because it draws afterwards, it draws over the one on the left side. Right? So now it starts drawing one on top of the other. This cube is a single draw of a particular dimension, like a single draw of that particular direction. Front direction of the whole vertex set. But it doesn't actually draw in the order. So doesn't actually draw in the order of what it visits, but just, whichever vertices the system starts processing with. So in this case, it processes these vertices. So as you can see, they look to be on the left-hand side. So we can see on the left, right? So since those vertices are drawn first, they are drawn over by almost anything else. And the one on the right side that we can see as a whole side is probably drawn the last. We can check this. So if we go to the bottom, and you can notice that is actually the side that is drawn. So this is the issue. We can see it in the bottom render, right? So just saying because people are not familiar with this. So just making sure people understand. Now, let's start with depth buffer. So what do we want to do? We want to have a set of images that are created when we start the whole process. So in here, when we have MISC data, because this is where we put all our data, right? Anything that is not belonging to a particular system ends up in this MISC data structure, which is just a way for us to keep data together. So in a given frame, so per frame, we'll have to create a depth buffer. Since it is per frame, we can simply create it inside the frame. I think that is a fair assumption to make. However, it will depend on the swap chain. I think that is fine. Or is it? How are we getting the images? Render device.swap chain current image index. Okay, so we're getting it through this. but we'll use it from frames for the back buffer because the presentation order, which is what the swap chains follow, that is the order is shown in the screen, and the back buffer order, which is what we draw on, can be different. Even the counts can be different. So, okay, let's do this within the frame itself. So what do we need? First, we need a VK image. This will be a depth image. And VK image view should be a depth view. Perhaps at some point, this too shall be mixed into the render device, but here it doesn't seem particularly necessary. So what else do we need? So every VK image view needs to be backed with a VMA allocation, which moves us to add that. So depth allocation. Well, with that, we should be good to go. So frame create takes a VK device. I think VK device is all we should need for the depth image, but we'll see as we go. So once that is created, all of this needs to be a part of the constructor since we're just doing simpler copy constructors. Not copy, but like copy all the data in type constructors. And similarly here, we have to add the same things. This needs can be const, so const it is. Okay. And similarly, we need to just initialize these. Depth image, takes depth image. I know this sounds like redundant, but welcome to C++ Learn. Okay, so that is it. Frame should be created from there. On this side, it says ambiguous symbol. That happens if we're including two things that shouldn't be together. And in this case, that is Volk and VRA. We always need to ensure that Volk is included first. This is coming up to become this is becoming like a issue that we have to keep taking care of. So let's clean it up as we go, which is Vulkan headers. Right? So we just create a single header called Vulkan headers. And now everywhere that we use both Volk and as VMA, we can just copy and replace it with, so include Vulkan headers.h. Ah, I see. So there's a small issue with the Vulkan headers. I will remove it, properly delete it, and then add it again. So a new item, headers. This is a small issue that a lot of Visual Studio projects face, which is Visual Studio just wants to create everything in the same main directory. It has to do with some Windows limitations. There's a limit in how long a path can be in Windows. And unfortunately, because of that, Visual Studio tends to avoid having deep paths and instead uses this filter. So these paths here are not real paths. These are fake. Okay, so first we have Volt, then we add VK. So VMA, VK malloc. Okay. With that, every place that uses Volt should be able to clean itself up. The thing was just called Vulkan header this time around. And you can see that's the same issue with model loader. So we'll fix that afterwards. So now this guarantees that Vulkan header is loaded. And what I'll do is I'll just look for all Volk.h calls. So entity manager has Volk and VMA. Include Vulkan header. I'll move it to the bottom there. And do it for every single place that we have these in. So all of these will be replaced with Vulkan header. right? And I'm gonna copy that and I'll go through each Volk. I do need to remove VMA, so I can't just like search and replace either. Why using Vulkan to render DirectX format? Well, I'm not using DirectX format. I'm using this little thing known as DirectX Math, which is just the library that comes with like the DirectX SDK. So it's not built for DirectX. It is just a math library. It just comes as a part of that entire toolkit. And the reason I'm using it is because it has full on support for SSE and other vectorization, which is pretty useful. So, why not? There is GLM, that's another alternative I can use, which is more or less built for OpenGL. But again, nothing's built for Vulkan. Not that there is any point in building something for Vulkan. It's just a math library at the end of the day. DirectX Math used to be called XNA Math. It was part of the XNA toolkit, but then they merged it with DirectX when they killed XNA. Rest in peace. XNA was great. If I need this protection, oof, I have included texture manager instead of Vulkan header. That's a funny one. With this is render device.h. Again, Vulkan header gets included. I'll just look for all instances of Volk and replace them with, okay, this one is fine. This is our own VMA implementation.h. It's probably a Volk implementation. No, there is not. But yeah, that's it. I think if I search again, so Control F, Volk.h, this should be, yeah, it should be fine. So build it once, see if it's compiling. There are a few warnings. We will fix that before we continue, like before we finish this, not the stream, but just the whole task. The stream will end early. I'm not going to have a long stream. I'm going to have a short stream, a break, and then the longer part, mostly because I can't handle like a long, I just came back from work, so can't handle a long stream all at once. It was unexpected. Okay. Sort include directives. Ideally, you should. But functional, this thing should be a part of those errors. Solved. All right. Let's come back to the point, which was to modify these frame stuff to add depth. That is depth image. We have to delete those because the ownership of depth images are on us. To destroy, it's going to be VMA destroy image. So the allocator would be render device or GPU allocator image take depth image take depth allocation. Take gets replaced here. Oh, I also have another reason why I'm using specifically DirectX Math instead of GLM. It's because DirectX Math just has these defaults that are nice and they work, while GLM needs you to configure things properly for all the features that you need. GLM is way more versatile. So if I was supporting, let's say, OpenGL and DirectX, I would use GLM. But since I'm only supporting DirectX, Vulkan and DirectX, I will use DirectX Math. I will be doing DirectX, just not on stream. At some point, I'll just start adding it in the back without nobody noticing. And suddenly things would work on DirectX as well as Vulkan, if I get time, if I have the energy and time. Destroy image view. Now it takes the device, take image view. Depth view. The callbacks, which are null. Okay, so this creates the we can destroy image view and destroys this. Both of these should be destroyed at that point. Okay, Now, what else to do? So every frame has to have all of these, which means all of those need to be created. We don't have enough data in the creation of the frame to be able to do that. So we will have to add that as well. That will come in the form of VK extend 2D. And I think it's swap chain extend. So we'll ask specifically for the extent of the swap chain to figure out how large does the depth image need to be. And now we can start creating it. So here we'll say VK or VMA, create image, takes the allocator so that I render. Ooh, we're not passing allocator, just passing device here. So now we'll have to pass the allocator as well. So VMA allocator. I'm keeping it as GPU allocator because maybe I want to use a different allocator later for actual memory, right? And this will be used here. So GPU allocator, create info. So that will be depth image create info, allocation create info, which will be depth allocation create info. The image would be depth image. The allocation would be depth allocation. And the allocation info is not very useful for us at the moment. Okay, now we've declared all of these here. We should declare the rest. So that's VK image, depth image, aka image view, depth view, and finally VMA allocation, depth allocation. Okay. So those automatically got constructed for us. We just need to create the create info. So VK image create info cost depth image create info. You can already see my keyboard full falling apart. Type image create info. There we go. Pnex is null. Flags are 0. Image type is 2D. So this is simple, right? Because we're using depth. This is simple. Format. There are 3 formats available to us. D16 UNOM S8, D24 UNOM S8, D32 S float, and D32 S8 UINT. What I'm going to do for now is just use the D32 S float and see if anything complains to us. If they don't, then good for us. Otherwise, we'll fix it. Mid levels is 1, array layers is 1, samples is 1 bit, tiling is optimal, usage is VK usage, so VK image usage depths. So you can see already there's a depth sensitive attachment option, just separate. Exclusive, index cube count. So that doesn't matter when you don't use concurrent. And initial layout. So your initial layout can only be image layout undefined. There's also another option which is pre-initialize or something, but we don't use that. Okay, so swapchain extend cannot be directly used because we take a 2D swapchain extend while the image create info expects a 3-dimensional one. But that we can fix rather easily. So with that, depth image create info is done. Now VMA allocation create info cost depth allocation create info. Time to set that up. So what are the flags? VMA, allocation, create, and I will add dedicated memory bit. So what is dedicated memory? VMA normally just allocates big buffers, big amounts of memory, and then sub-allocates. So when you ask for some part of it, when you ask for an allocation, instead of allocating a separate allocation, it will give you a part of that memory, which is good for you, right? That's better for the GPU to handle as well. What we will do here instead is we'll say, give us a dedicated memory, give us a separate piece of memory instead of doing sub allocations. And the reason for that is because depth images are generally resized kind of often, and they are effectively used in a different way from everything else. Both depth images and the images where you render everything, so color attachment. Currently, we are not using separate attachments, we're just using swap chain. But once we actually do that, we will also use dedicated memory for those, because we want each of these images to have their own allocation, to be able to be resized easily as the screen resizes, and to not waste memory, because otherwise VMA might add extra memory. So maybe it will give us enough space to do 2048 by 2048, but our images are 1080, 1920 by 1080, right? They're not efficient at fitting inside that memory, while normal textures are square. So those would be fine. So I can say this is usage. I can say GPU only. I could say auto, but I'd say GPU only because I know exactly what I want out of this, right? Required flags, 0. Preferred flag, 0. I don't particularly care here anymore. Memory type, I think VMA memory type. I think it's a VK memory type. Anyway, 0. Pool. So let's check the docs again. That's seems like okay, wrong direction. If it's not null, then the above ones are ignored. Memory type bits, 1 bit for each memory type acceptable for this thing. Value 0 means any type is accepted. Yeah, that's precisely what we want. So pool is null pointer, user data is null pointer as well because we don't have any. Priority is 1.0. Okay, so that's depth allocation create info, and that should be fine. Can be made const expression, so we make it const expression. This one cannot do that. So that creates the image for us. We have to do a check on this. Again, one of those things I consider we can't solve if we can't do. But inside texture manager, we already have image view creation, and it automatically creates like the default image view. So we can just copy that particular thing. I think it's a part of create texture right there. And image view create info comes from here. So I can copy that into the frame. This needs additional things, doesn't it? Let's add them already. VMA allocator, GPU allocator, and VK swap chain extend. VK extend to be swap chain extend. And we go in there. So we have swap chain extend right there. This can be const. And after this, we can create the image here. All right. So what's the MIP levels? It's just 1. So it's a constant value. This can be const expression. So let's do it. Image texture. In this case, this is depth. Image create info dot format. So that is depth image create info dot format, which is whatever format we put in there, right? And I did not copy that one. Create image view. Anyway, it will be simple enough because we already have the image view create info. Callbacks will be null. Image view will be depth view. It should be a pointer. Check. There we go. Right? Now we assign things. So frame depth image equals depth image. Depth view is equivalent to depth view. Frame depth allocation equals depth allocation. And that's it. View, image, view, allocation. Three things that we wanted, three things have been added. So those are depth. Everything related to depth that we needed. We have already written the destruction function for this. So nothing else needs to be added in the frame itself. So now we can go to the Blaze, like the main thing, main function. So in here, we will handle all of that. So the attachment info will now change. So what's happening here? We say there's one attachment info, which is a color attachment. So here's the depth attachment, and we need to create that. So I will add a second one. This one will be called depth attachment info. So depth attachment info. How do we get the depth attachment? Also simple, current frame dot depth view, and we don't need anything else. These are important. So the image layout is actually image layout depth attachment optimal. To be fair, it shouldn't matter. It should be undefined actually, because what we get is undefined, right? Resolve image, we don't have any. No resolve. Load up clear. Store up store. That does sound right. Pnex, that is fine. Clear color. So I've said black, but it is not a color anymore. So this is going to be depth stencil value. So that changes because it's not a clear color value anymore. So we take clear depth stencil value. Const expression static depth clear. And there'll be an interesting question here. So what is depth? Where does it go from and where to does it go? Does it go from 0 to 1? Does it go from -1 to 1? Does it go from 1 to 0? And there are different ways of handling this depending on whatever your rendering engine wants to do. In our case, we will say depth. We will clear it to 1.0, which is the furthest depth possible for this engine. And stencil will clear to 0. We don't have a stencil, so it shouldn't matter, but we'll say it anyway. So that's depth info, and we have, where did color info go? Did we forget? Oof, I think we did. So I'll copy that and undo. Too far. Yeah, I'll undo the thing, add that back in, and I just need to create a depth clear, so I'll redo that as well. It's retrieve depth clear. Okay, clear depth stencil value, depth clear. Instead of float, 32 is just depth. Whose value is equivalent to 1.0. So what I'm saying is the furthest depth possible. So anything that's closer than that will get rendered. Otherwise, we will be in some big trouble. So depth stencil clear, as I renamed it. And for depth attachment, we pass it. So as you can see, there can be multiple color attachments. There's a count for that, but there can only be one depth attachment. So with that, we've created depth attachment. Everything here is fine. What is not fine is inside the MISC data. So when we create the pipeline, we need to ensure that the depth is actually being used. So depth bias, we don't care right now about depth bias. We want to go for stencil state. All right. So depth test enabled, false. We need to make it VK true. So now to start using the depth buffer. Depth write, also true, because we want this pipeline to write back to the depth. There are ways to do depth write false, but depth test true, which means anything you write will not modify the buffer, but will render in the correct order. You use it often for transparency. Depth bounds test, we don't particularly care. And compare op has to be done because here we'll say less. So if the depth value is less, then it's true, otherwise it's false. We can do greater if we reverse the directions, right? If camera is at depth 1 and if far location is at depth 0, then we will do greater. Okay, this should just work now if I run it, but we'll see what's happening, right? Frame create is not complete because device, then it needs the GPU allocator, and here it needs the swap chain extent. All of those are already available, so I don't actually need to do a lot for that. Okay, depth is still not working. You can see there's an issue here. So what's the problem, right? Must have image aspect depth bit. I see. So I made a mistake when I was creating the frames. So when I created the image view, I just copied whatever was available to us. But here it shouldn't be color, it will be image aspect depth bit, because we're not caring about color, right? We care about depth. What else? Depth only, that's fine now. Image layout is undefined, must not be undefined. So then this one comes from command begin rendering for the depth. So we need to actually create the depth. Set the depth to that value. Let's go. Where is it? Are we in the right place? No. Depth. Okay. So here, depth shouldn't be undefined. This should actually have a layout. So layout, depth, attachment, optimal. Okay. I'm just going to run it again just to see what the new warnings are. There will be some. There we go. So SFloat must match the corresponding one for depth attachment format, which is format undefined. Because when we created this structure, we did not create it here. Where did we create it? Hold on, where is this? Then the pipeline rendering create info. Yeah, because the pipeline itself doesn't expect depth buffers. So depth info. Pipeline rendering create info, color attachment count, depth attachment format equals VK format D32 SFloat, right? We have hard coded this. This should not be, because different computers actually have, like, different GPU vendors have different formats that they prefer. So based on that, we'll have to ensure that they have different ones. Okay, there is something weird happening right there. That does make sense. So depth is working. If you can see, it looks a little weird because it like intersect and quickly swaps positions. But anyway, close that just to see what the warnings are. So no warnings now. And you can see the depth is working, right? Orders of depth are correct, even though they look very weird because they just flip colors because they have similar textures. That's depth buffering for us. All right. Depth is done. What I'm going to do is I'm going to quickly just pick out the parts that we did for depth and make sure that it is added to my Git. I'd like to keep each commit separate. So we'll ensure that. This is for the depth stage. Again, this one for the depth. This is also fine. Put a stay stall. This is the entirety of the thing anyway. Frame.cpp, let's see. This one. Yeah, so all of these are pertaining to depth, so it's a stage all. I need to format those as well, but I will do that in a second. What else do we have to add? So here in this, we've added Vulkan header, so we will put that up as well. We've done it here, so again, it will be a part of the change in the stage all. Race.cpp. So all of this is not a part of the current commit. This is, so I will add this. And attach stage grid info here. Sometimes the speed of this annoys me. Okay, it's not really the speed, it's more to do with what I'm working with here, but still. I'm very used to just doing this quickly with Magit on Emacs. The fact that I don't have that available, I have to use this GUI that doesn't seem to work all the time, like consistently. Is a bit annoying. Okay, so we already looked at this one. We didn't stage this, so I'll stage it quickly. Functional. We did not need functional. Which one is this? Blaze.cpp. This one we don't need. That one got added as a part of. Yeah, okay. I need to click in the file before I can use it. That's okay. Miscellaneous data as a note more. Yeah, that's precisely how it works. .NET. Send the device.h. There we go. Vulkan functions. All right. Texture manager.h. Also good to go. Net device CPP. So GPR locator will have to be added there. That is also a part of what we need. This I need to remove. So again, stage the removal. The rest have changes as well. Things I can't necessarily correctly filter. So this I can. This I can stage. Model loader I won't. Model loader here I won't. Filters, again, model loader I won't filter, but Vulkan header I will filter. So this works out for us. That I don't. Model loader I'm not adding at all. This one only has CGLTF, which is also part of the main code. So with that, if I'm correct, it should be the right things. This is a set of stage commit. I will say depth buffers added. We will commit staged. Hold on, there is a fetch coming, incoming fully bindless textures. They seem to have diverged. That's fine. We'll push by force whenever we do it. Now the question is, does this? So I'll stage it. Then once it's staged, I can do stash. So stash all. Once I've stashed it, I can build and run just to see if that particular commit actually runs or not. One failed. This model loader could not be opened because the header file here required model loader. And it seems I might have committed. So that's one fix to be done. Amend, commit staged. Okay, build solution, start. Okay, and that's depth buffer, right? So that seems all right. I'll just go to the solution and I'll run cleanup on all of these just to reformat all the code to ensure that everything is up to spec. Uh, we can see not everything is up to spec. So good changes. Let's see what's up. There's a reformat in the memory. There is a reformat in the textures. This we will stage. It's not textures, but this thing. Frame has again a reformat. Also stage it. Global memory. Let's stage it. Texture manager. Stage it. Working header. Stage it. Amend commit stage. So now that commit has everything correctly. So then I can just apply all changes and restore staged. And unstage all of them. Won't work because one of the things was changed. Model loader was not included in Blaze anymore because I manually removed that. So inside Blaze CPP, I need to add model loader here to include the /model loader build, and now it should succeed. And we've got us back to the point where we have the cubes. Cool. Let's continue from here. So, what do we need in the model loader? We needed to be able to actually load all of these nodes and transforms into the entity system that we already have, which means the entity system that we have needs to be modified to support each of these meshes. Now, one of the things is entities will need hierarchical transforms. So what are hierarchical transforms? It's when each entity has children, and when an entity is rotated or translated, the children also rotate and translate along the entity. So if you have something at 0,0, and the child of that particular thing is one unit in the y direction, then rotating it 90 degrees, rotating the original parent in 90 degrees, should move that particular object away from y-axis into the x-axis because it will rotate along the parent's axis, or in other words, the parent's frame of reference, right? So all children will always remain in the parent's frame of reference. Oops. And we have to behave according to that. So this means entities themselves need a bit of modification. Currently, entities have transform, mesh, and material, and that is the start and the end of how they're constructed. And they're not even loading newbies. What we will want to do is we want to add another thing, which is like children. But since an entity can have multiple children, it would be a variable length of entity children, like n children. And then we'll have to allocate this array or make it a vector, whatever. Point is, the allocation can get a little painful, mostly because each entity will be jumping around to find the array of its children whenever it's allocated, because it won't be allocated alongside entities, because entities are all in an array. We'll go to the children array and we'll jump back to the entity array. This is fine. That is one way we can do things. So this pointer will just point into another one, which will point to the children. So in which case, it's more of a pointer to pointer of children. So this can be done. It is probably a simplistic way to do this. And the other option is to create a linked list. At any point of time, the traversal of these will be either from a parent to all its children or from a child to the parent. So each entity needs to know who its parent is, right? Like, you know, do you know who my father is, sort of thing? And it needs to have all its children, but it doesn't need to have each of the children in the array. It can just say, here's my eldest child, and he'll tell you everything. So we can actually say child, first child, and then just, or actually, it won't be the first child, but just child begin. And it will just be a linked list that will continue. Of course, it means each entity element is inside the linked list. Therefore, you will have to have each entity with a sibling. So, next sibling. Do I need double-ended entities? Not necessary. And I'll need a parent, so n parent. Okay, so this is the other option. Which of these is likely a better thing to do? I don't know. We will have to use it and then figure out which one is the better one. But just for the sake of simplicity, I will use entity array for children for now. It makes it easier on us for just creating all of these. Of course, it means each of the children needs to be able to be a part of this structure. So we need to allocate enough data for it. So here, as you can see, there's an entities array. We also need something that will allow us to create an array of entities. So what I will say is there's an entity pointer children. So what is this going to do? Each child can only have one parent. That is guaranteed to us. It's a tree. Which means at any point of time, the number of children cannot exceed the number of entities. So I can just create this array, which is of the same length as the length of entities, and be able to use this. Are there any flaws in this? So there is. If I try to add a child to an entity, it won't work if there are, like, if the first entity takes up slot 0, 1, 2, the second entity might take up slot 1, 2, 0, 2, 3, 4, 5. Second entity might take up 3, 4, 5. And now I'm stuck because the first entity cannot add more children anymore. Hold on, I'm just going to try something new in the stream. Milton. There we go. Let's see. Is this working? It seems to be working. So let's see. So we have a parent. Color is all wrong. So we have a parent P, right? This has an array here. Array has slots. So there's 0, 1, 2, 3, 4, 5, 6, and 7, right? 8 elements is enough for us. Parent is 1. Then there is, so actually, how do you get to arrays? Interesting. Okay, that worked. So let the entities array be. So this is children array. This is entities array. Again, you have 0, 1, 2, 3, 4, 5, 6, 7. So this is parent 1. This here is child 1, child 2. This is parent 2, child 1, 1, 1, 2, child 2, 1, and child 2, 2. Right? So what happens is parent 1 points here. Here it points to child 1, 1, so it points there. Here it points to child 1, 2, it points there. Then parent 2 actually points here, which says child 2, 1 and child 2, 2. So this points there and this points here. Now the problem with this is the moment I try to add a child 1, 3, this can't be added here without having to move these. And if I move these, the pointer here becomes invalidated, right? So this becomes invalidated. So this won't work. So just coming back to the thing I did before, I don't actually need to erase all of that. I can just use it again. So coming back to the linked list idea, what I can do is I can say you have such a structure, right? Each of these has a parent and everything. So we've got a set of parent-child relationships. In fact, I can erase that. So what you have is a parent-child set. So you've got a parent P1, you've got a child 1, 1, child 1, 2. We've got this connection. These are actual relations. P2 has child 2, 1, child 2, 2. Maybe even add a bit more for this. So instead of child, like we can put grandchildren, right? So it's 2, 1, 1, G2, 1, 2, and G2, 1, 3. Okay, so you have this kind of a setup. What we can store, because we want constant space, we don't want extra allocations, is we can store one thing which goes the first child, so child, similarly the first child, child, first child, child. There will be a secondary relation to this, like a complement, which is parent. So parent, this one will have a parent. So we have a parent. This is almost like a linked list, right? So this creates a double-ended linked list. And then we create a second linked list, which goes from a child to the sibling. So that is how it will go. And now with this, what we can do is if we want to add a child 2, 1, 1, 3, a third child in that sequence, we can just say, okay, we cannot add it here conveniently. So instead we just say, cool, we add the child here. So C13, we point it to C12 because we know the first child. We'll add that relation. And done, right? This goes away. This goes away. And that will automatically create a new child array for this. It's a linked list instead of an array. And we can always sort it to compact the data if we need to later on in our process. Yeah, nobody's gonna kill it anymore. So instead of children array, let's do the thing that I said. It also saves this extra allocation there. So instead of saying children, I can say M parent, entity pointer, M child. Should it be child or should it be next? I mean, it has to have a child. Let's call it child head. Entity M. So you have the parent, you have the child, you need the sibling. So it's next sibling. I'll make this first child. So first child. We don't even need a child count because the next sibling on that particular child will be empty. And that allows us to just go through the process. Is there a possibility that we need breadth first search? Perhaps if we need it, we can add more things into this. Now, these are 8 bytes each. Do we actually need 8 bytes? All of these entities are within the context of the entity manager. So they can all be indexed into the entity manager. currently we do return an entity pointer. So let's keep it consistent and keep it like this. But I will put a to do. So to do switch to entity IDs or index, right? Now with that, we can continue moving on. Do we have any issues with alignment? So let's check. Transform, the size is, so this one requires 16 byte alignments. So this whole structure requires 16 byte alignments. This is already 16 bytes, so this is fine. 16 byte alignments. Mesh needs nothing additional. 8 plus 8. So this is 24. Size of mesh should be 24. So let's write this down. 32. 64. We can also assert this. So static assert size of transform equals 32. Size of mesh equals 24. So that's not 30, that's not this thing, it's 56. Material has a texture ID, which is an RID 32. 32 bits, 4 bytes. And sampler is 8. So this actually has a padding in it. So ID is 32 bits, right? RID is 32 bits. So with that, this is 8, this is 4, that's a total of 12 with an alignment requirement of 8. So materials will probably be 16. So add 16 to this, that's 72. We can test it. Material is in fact 16. So we are wasting space here. Fix wasting space. Parent is 8. So this is 8 more. So that's 80. This becomes 88. This becomes 96. 96 is in fact divisible by 16. So our alignment requirement will be fine. We won't have any patterns. So that is fine. Right? All right. So once that is created, these will just be null when we construct an entity. So here I'll say M parent is null, M first child is null, M next sibling is null. They'll just simply be null, and we'll be able to set these. How do we set these? So first there will be a setter for parent. So void set parent. It will take an entity pointer, parent, and it will say M parent equals parent. That's it. But if you set a parent, it also means I need to insert myself into it. So what I will do is first I'll check if M parent equals parent. If it was already there, we return. Otherwise, insert self into parent. And we'll also remove self from parent. So if parent equals parent is one thing, then if M parent is, if it doesn't exist, so if there is parent, sorry, then remove self from parent, in which case what we will do is we will take our sibling and we'll remove ourselves from it. That is tough. It's not convenient. So double-ended is in fact better in this particular case. It will make sense. It pref sibling 96 and that becomes 104. which is no longer divisible by 16, if I'm correct. So if I'm right, this will tell us that it needs a bit of padding. Oh, it straight up gives us an error. Why? Because it cannot assign this to the material because sampler is now in the first position. Okay, build solution. This was fine. It doesn't give us a padding overlay, which is interesting. Because there's nothing we can do, I suppose. It's here you are wasting space. U32, I'll make it explicit. So padding 0. Build the solution. Static assert size of material equals 16 still. And it is. So that means this padding does exist. I could be there. All right, what's next? After 104, to make it again 16, like 16 multiple. Hold on, did I do something wrong? 96 becomes 104 plus 8, so 112. I have another 8 bytes. I can add something if wanted. Don't think there is much to add here. So let's check this. Size of entity static assert size of entity equals 104, which is what it should be at the moment. We put it here in the bottle. It's not actually 104. So what is it? Oh yeah, it is 112 because it will pad itself. So I'll again make this explicit. I'll say U in 6040 and pad M 0 112. And the static assert is still valid, right? So that's kind of it. Again, this padding has to be is wasted. So I will say it's wasted. And we don't need these anyway. So off they go. All right. Now, when you set a parent, you have to remove self from parent. The way you do it is you simply look for the previous. So you specifically just look for the previous node in the system and you exchange the pointers. So M next sibling, M previous, which will be yourself at the moment, will actually be replaced by your previous sibling. Next siblings, M. So now for previous sibling, the M next sibling will be M previous sibling, right? Previous sibling can be null, next sibling can be null. So both of those cases need to be handled. So if M next sibling, then you do that. If M previous sibling, then you do this. You set by parent, replace prev of next with prev of self, replace next of prev with next of self. And by doing so, we've removed ourselves from the equation. And here I do want to do something. So if I don't have any, if I don't have a previous, means I am the head of the chain. If I am the head of the chain, it means the entity needs to also change its head. So if previous sibling exists, then we change it. Otherwise, we are head of chain. And so if you will have to remove parent's own thing. So M parent, M next sibling, parents, no, it will be parents first child equals M next sibling. Did I make a mistake here? I did. Okay. So now what is happening is we'll just move the parents pointer, like head of the chain ahead, if we are the head of the chain. By doing so, we've extracted ourselves from the parent as well. Finally, M parent is null, but we don't particularly need to do that because we automatically insert ourselves into the parent here. And the way we do that, we take the parent's first child, so first child, and we say our current next sibling is the first child. So we point to the first child. Then for the first child, so we take that. All the should be older than 10 again. Yeah. So we take the first child and we say the previous of this is ourselves. So that is us, which move this pointer, parent dot first child. So previous sibling is ourselves. The next sibling of that thing doesn't change. Each parent doesn't change. So all it has to change is say there is someone behind us. For us, we say there is someone ahead of us. And finally, M parent next. So M first child equals this. So we put ourselves at the head of the chain. So now what I can say is old head is next after us. After this, I'll add this here because it makes it a bit easy to see. I will change that with old head. So I'll say entity pointer old head. Which allows me to just say old head. Old head. So old head's previous sibling, which is this is prev to old head. And finally, we are the head now. Woo-wee. And with that, we should have inserted ourselves. Now, another thing we might have to do is add a child. So void add child from an entity parent. So entity pointer parent. What do you do when you add a child? Add a child, and this will be child. Is you take the child and you call set parent on it and you give it this. So one of them is going to be simpler than the other. Like we just have to choose one of them and the other one just calls the other one. So we don't have to actually do double implementation, let's say. Initialize members, build signaling is this, padding is 0. Yeah, all of that is fine. Material is never moved. It is forwarded. What are you talking about? Oops, wrong buttons. Okay. What has happened now? So we've added parent, we've added child. We want to be able to remove child. So remove child. How do we remove child? So entity pointer child. We tell it which child we need to remove. And we do it by removing ourselves from the parent. This here is remove parent. Remove parent, parent. Actually, we don't need a parent, but just that. Void, remove parent with this, right? So that just removes the parent from us. Hmm. Here yourself from parent, all of this is done. We also need to clear out our own mix. So M next sibling equals null pointer. M pref sibling equals null pointer. M parent equals null pointer. So at the end, we ended up writing the parent anyway. Okay. So with this, everything is has been set. And remove child is nothing but the child saying remove parent. We could do this other way. We could write everything from saying that the parent is the one doing it, right? And then remove child will be nothing but calling this on the parent. But yeah, we'll say assert child will guarantee if child exists or not. Remove parent, we can say it just works based on that. Set parent, again, we'll assert that it actually is giving us a valid parent. That should be it. Remove child is can be static, but in reality, remove parent would modify ourselves. So doing that is kind of not good, as it violates the const principle then. Okay. Nothing really changed. Like we didn't actually change anything in the process. We just added this whole thing about set parent, but that was about it. Phew. Continuing. So once this is constructed, we have an ability to add parent and all, but we don't actually use them inside our construction system. And we have this big padding here, which is not used for anything. What I can say is I can make it a flag. So I can say M flags. Fix me wasting space that I can keep. But I can make it 32 bits. So I can say UN 32T and modify. 12 plus. I don't need it. I don't particularly need it. So fine. Let's leave it like this. Now, when we iterate through all the list of things, we will have to do some complicated stuff to actually do this level of handling. So what we can say is when we try to render things in place, where is it? Here. Instead of going through every single entity, we will only go through the parents. So we'll say for all entity, if entity dot, oh, we don't have any way of getting if it has parent or not. So I will just say root and just return a boolean here. So I'll say bool whether this returns is a parent or not. So is root. This is const and it returns not m parent, right? So if it doesn't have a parent, then it is root. And we'll add no discard. We should always add no discard. Should have been default, but welcome to C++, where we have backwards compatibility to infinity and we just patch everything in. So let's continue. So entity, so if entity dot is root, if not entity dot is root, we continue. So children will never be accessed through this iteration, okay? And inside this, for drawing, we will then iterate through children. So we will extract this as a separate function. So we'll say this is draw draw entity, which is, oops, actually this would be auto draw entity equals, takes a function there. It's a lambda that does this. It takes an entity as entity as a parameter, right? So what do we do here? So we draw entity first, draw entity, entity. That is a const. This is not a const. So we'll take it as a const here. Draw entity. Done. And we'll create two of these. So this is the world transform for this particular entity. We'll create a draw entity which has nothing. And then actually we'll just overload it for now. XM matrix. So it takes a matrix. Should be FXM matrix really, which is parent. So it takes a parent transform. Copy for each location, consider passing by const reference. Parent is never used. Okay, const reference it is, if you say so. I thought FXM matrix was already const reference. But anyway, so we take an XM matrix. And for each draw, once we're done drawing, we will go through the children of this thing. So for the children, the way we will have to operate is that's a little issue. Cd function returns a void, takes an entity const and a directx xm matrix constant. This function actually doesn't need it because it can derive the template parameters. So entity and parent is directx xm matrix, right? XM matrix identity. That's the default for the parent. And so for draw entity, what we'll do is we will simply call for each of the child. So entity dot children, which we don't have here. So we'll go into the children thing inside entity manager. For an entity, we'll call it a struct entity iter. It seems I will have to go. I will come back in around an hour to continue on this. And we will make a few changes later on, but first we'll just get this working, right? So I'll leave this as a to-do. Thanks for coming. We will continue in 1 hour. See you, everyone.